Quantum computing will excel at large optimizations that challenge classical systems. One such mammoth problem is power grid energy distribution. How has one neutral atom system started to tackle this already? Find out in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CEO of Atom Computing, Rob Hayes. Welcome to the show.
Thanks for having me.
Yeah, tell us about how you found your way to quantum computing. I know there's definitely some chip history in your past.
Yeah, my background's a little bit different than a lot of the kind of founders and early pioneers in quantum computing. My background's actually in computer engineering. I got my degree in computer engineering at Georgia Tech and went to work at Intel. Worked there for many years, doing microprocessor product line management. Eventually, I was the executive in charge of the data center silicon portfolio for Intel's data center business, and then basically leading the roadmaps for the server processors. So I had the benefit of working with a lot of the large cloud service providers around the world, server OEMs, as well as high-performance compute centers, and kind of see the world of computing from the classical computing side. And it was clear that over the last 10 years or so, with the advent of GPUs and AI accelerators and other things like that, that the world had really moved to kind of a hybrid compute type architecture, and quantum computing was on the horizon and seemed like a clear kind of next wave of computing that could fit into that kind of existing hybrid compute cloud infrastructure that's already been built out. And after Intel, I went to Lenovo as chief strategy officer for their data center business for a few years, and got involved with Atom Computing as part of Lenovo. I joined the board of directors of Atom Computing, and then a few months later, was invited to join full-time as CEO, and I jumped at the chance to do that. So that's how I ended up at Atom. And luckily for us, we've got a team of folks that are world-class quantum physicists and engineers and know how to build quantum systems. I know how to run a computing business and plug those into the infrastructure that exists. And so I think my skills are complementary, but quantum is something that I'm learning, on a daily basis. It's been a lot of fun.
Yeah, and of course the whole classical world isn't going anywhere. The two are going to work hand in hand forever. I mean, pretty much.
Absolutely.
Yeah. So tell us a little bit about Atom Computing. What you guys do there, what your goals are.
Yeah, so Atom Computing is a quantum computing hardware platform company. We've been around for over 5 years now. We were founded in Berkeley, California. We've since expanded our operations into Boulder, Colorado. The team is split about 50-50 between those two locations. We're building our quantum computers out of optically trapped neutral atoms, one of what a lot of people consider a newer modality. The technology's been around for a couple of decades in academia, and us and a few other companies have started to commercialize that in the last few years in various applications. So we're focused on universal gate-based quantum computers. We chose neutral atoms not only because the team has expertise in this technology, but we think it's quite scalable relative to some of the earlier modalities with superconductors and conductors and trapped ions. And so what we're trying to do as a company is just simply take that technology, scale it up, make really high quality qubits from coherence, fidelity, gate speed, all the performance metrics you expect to see in a competitive quantum computer. And that's what gets us up in the morning, is just driving towards that mission every day.
So yeah, we'll probably touch a little on scalability. But first, can you explain for our listeners the difference between neutral atom and trapped ion? I guess at times they might sound similar to people who aren't used to it.
Yeah, I mean, an ion is an atom. It's just a charged atom, right? So,
yeah.
Honestly, they're close cousins, right? Mm-hmm. What's different is how you capture the atom or the ion, how you trap it. What you do when you manipulate it, the energy levels and the spins and things like that are fairly similar. But the biggest difference, I'd say, is in a trapped ion, you're actually building a trap. It's like a chip that has electromagnetic fields that have the ion kind of suspended in free space between these electromagnetic waves. In neutral atom system, you're trapping the atoms. They're not charged. They're neutral atoms, meaning they've got the same closed outer valence. They're trapped with optical tweezers in basically a wavelength of light. And so they're also in free space, but we're using light instead of electromagnetic waves. And we're doing this in a vacuum chamber in free space. So there is no chip, there's no trap device, if you will. And that actually creates another key difference in that with ion traps, there's a finite amount of ions you can load into each trap. And then once you hit the limit of how many ions you can fit in that trap, then you have to connect multiple traps together with some kind of a bridge or an interconnect, typically a photonics type interconnect. Neutral atom systems have the potential to scale up to hundreds of thousands and even millions of atoms or qubits in one single vacuum cell. So the need for these interconnects and bridges between modules is much further out in time for neutral atom systems than it is for trapped ions, which gives it that's what gives it part of this scaling potential.
Nice. Yeah. So it's like a 3-dimensional array that you're able to create in there.
Yeah, you can create 2-dimensional or 3-dimensional arrays. Today, our systems are 2-dimensional, but we're already working on prototypes for 3 dimensions.
Okay. And would you say that the optical tweezer inherently leads to a like higher fidelity qubit, like less noise?
I don't know that the tweezer is necessarily what's going to lead to higher fidelities. At the end of the day, you need to get noise out of the system. Mm-hmm. Neutral atoms are good because actually they are relatively immune to outside noise because they are neutral atoms, they're not charged particles. But there's a lot of engineering work that goes into getting fidelities higher because there's lots of sources of noise and you want to get all of those out of the system as much as you can, and have very high precision control of the light that's going into the platform. So precise amplitude, frequency, phase, and all that. It's all about precise control of light in order to get fidelities up, and that also helps you scale up to larger numbers of qubits as well. More precision you have, the more control and the more opportunity to scale up with high fidelities.
Cool. And the reason I wanted to have you guys come on now is some news that you're making recently. So there's a collaboration with the U.S. Department of Energy's National Renewable Energy Laboratory, or NREL. Can you tell us about this collaboration and how it got started and what it entails?
Yeah, so it's kind of an exciting collaboration for us for a number of reasons. What the collaboration is the NREL, which is what they're known as. They have basically it's a high performance compute platform that they call ARES. ARES stands for a longer acronym, but basically this is a high performance compute platform where they've created a digital twin of the U.S. energy grid, and they're able to use this digital twin to simulate different scenarios or different choices that could be made in optimizing the grid. They can bring on new sources of energy. They can bring on new demands or loads of energy. They can bring in new pathways and lines and things like that in this digital twin. And they can kind of test out different scenarios and see how the grid might respond to those scenarios or choices that get made. What we've done is with NREL, is integrated our quantum computing technology stack in with this ARES platform. So they really, for the first time, have this kind of hybrid HPC ARES platform with quantum offload capabilities so that they can make calls to our quantum system and explore different computations that really just wouldn't be tractable in the current platform. The other thing that I think is really exciting about it is this is really just I think it's a good example of a public-private partnership. Mm-hmm. Where we're bringing expertise to the table in quantum computing and how to program them. They're bringing expertise to the table in how to manage energy grids and the complexity of that entails. And by bringing both teams together, we're able to really collaborate and try to move the ball forward on solving very tough, complex problems that just weren't solved before. So I think it's a good model. The other thing that's kind of exciting is network optimization problems in general, which this energy grid kind of use case is an example of, are a really good use case for kind of early adopters of quantum computing. And there's lots of network optimization problems across lots of different sectors in the government and industry that could be able to take advantage of some of the similar results and algorithms. Telecommunications networks, transportation networks, supply and logistics networks. There's networks across many sectors, and a lot of the learnings that we get out of this energy grid simulation and modeling could apply, to other sectors as well. So for all those reasons, we're pretty excited about this partnership that we have with NREL.
So it's pretty interesting. Some of our listeners might not really know what a digital twin is. I mean, they can, of course, infer. What's the scale of a typical digital twin? Like you hear about toy problems in quantum computing a lot, in use cases. So just if you could just like frame that for the listeners so they understand.
Sure. I mean, in general, a digital twin is a simulated copy in the virtual realm of some physical system, right? So in the case of NREL, they've basically taken the energy grid network, which has, lines and nodes and switches and transformers and all these things, right? And they've basically put that into a simulated environment on a high performance compute cluster. Other examples would be like if you're Lockheed Martin or Boeing and you're building an airplane, you would build like a digital twin of the airplane that you could use it to simulate how it might fly in different scenarios, or even for maintenance or other type records, so that you could kind of know how it might be aging over time, or respond to upgrades and things like that. So digital twins have been around for a while. The scale of the one that NREL has is really the scale of the U.S. energy grid. Like that's kind of their mission, is to make sure that they're understanding how to best optimize energy production and transmission in the United States from a research perspective. They're not the operators. And then take those learnings and that research and transfer that to the operators, the power, the power companies and the power grid operators, so that they can better improve the way that they manage their infrastructure, upgrade the infrastructure, produce energy, and those kinds of things. So the scale of this Ares is really trying to simulate the overall U.S. energy grid and looking at different aspects of that. What they do on the quantum platform will evolve over time. It'll start probably pretty small, asking some pretty straightforward questions around like power line failure and how they might reroute power in a more optimal way and things like that. But I think they aspire to ask bigger and harder questions over the long haul as these quantum systems become more capable and they learn how to program them and get results out of them.
Okay, so folks can visualize, it does have the number of parameters to simulate the actual grid, let's say, but you might be zeroing in on some aspect of it as part of a experiment.
That's
basically.
right.
Yeah. Okay. Yeah, that makes sense. So this is an interesting use case because you want to try and be able to extrapolate to other similar types of use cases, right?
Yeah, exactly. If we can optimize how energy flows through a grid, why would we not be able to optimize how bits flow through the internet or different telecommunications networks, or cars flow through roads and things like that?
Yeah, so you can apply the learnings. So what would make this collaboration unique? Has anything like this ever been done before?
Well, I think a couple of things make it unique. To our understanding, it's the first time anyone, in at least this use case in energy, has done an integration between an HPC system and a quantum system. So from a technical, hardware platform and software API perspective, we've blazed some new ground there. We also just think it's a really good, kind of back to that public-private partnership. Certainly, this is not the first public-private partnership in the world. But we're early days in quantum computing, and there's not a lot of examples of national labs doing research projects at the application level like this with quantum computing companies. So we're early days on that, from the industry being in its infancy, but we think it's a good model. We'd like to replicate that in other areas over time, and hopefully we'll have a lot of success in this one, and that success will inspire the next wave of programs.
Is there anything you could tell us about what this looks like, this collaboration? Like what type of hardware you're using on your end to like enact some of these simulations?
The group that we're working with at NREL is in their Flatirons campus, which is just down the road from our Boulder, Colorado office. Oh. So we happen to be neighbors.
That's great.
Which is great. That allows for easy collaboration when we're physically close to each other. The integration that we have is at first level, at the software level. Our APIs and emulators and things like that have been integrated in with their platform. That will give them access to our hardware platforms. The platform that we have today is a prototype platform in California, and then we will, when they become available, layer in or give access to our next generation systems that we're building in Boulder, Colorado as well. But that's a future statement.
Okay. So for folks who are used to talking in qubits, like how many neutral atom qubits would be, used in something like this?
I think that's a great question for NREL. Is like how many do they need for their use cases? I mean, more is always better, and the more you have, the more complex system you can build. The current platform that we have is 100 qubits. The
Hmm.
next generations are quite a bit larger than that. We haven't announced publicly yet, the specifications for those systems. We'll be doing that in the coming, weeks and months. Um, but long term, really, everyone's got their eye on fault tolerant quantum computing. We're in this era now that, as your listeners are aware, the NISQ era, the noisy
Hmm.
intermediate scale quantum computing era. Optimization problems like this are a good candidate to explore in that NISQ era. But ultimately, we want to get to large scale fault tolerant quantum computing. That's the long term mission of our company. I think that's one of the reasons that partners like NREL, but others, are very interested in working with us because they can see our roadmap, they can see the progress we're making, and how fast we're able to scale up these qubits. And that gets people very excited about working with atom computing. And so, yeah, that's kind of the plan moving forward.
So would you say that running this kind of experimentation has like a bidirectional flow of information when it comes to improvements and things? Like, are there benefits that they're getting, benefits that you're getting from doing something
Yeah,
like this?
absolutely. I mean, I guess I said one of the reasons a public private partnership like this makes a lot of sense is that we bring our expertise, they bring their expertise, and together we can do things that we couldn't do separately. And I think the learning we get from that is just as important, right? Because we learn from working with customers and partners like NREL. How do they use the system? How do they program it? What results do they get? Where do they see performance bottlenecks or performance gains relative to competitive platforms? And that learning helps us improve our products and make different design choices as we move forward. Because just like any product company, you want to make the best products that delight customers as you can.
Hmm.
And so getting that learning from them is invaluable to us. And I think that the learning they get from working with our quantum applications experts and software teams gives them sort of a jump start in figuring out how they can take advantage of quantum computing to solve some of these complex network problems that they like to go solve. So, yeah, I think the learning, bilateral learning, is a really important part of this.
So you see a potential for improvements all up and down the stack as a result, like by identifying
Absolutely.
those
Yeah,
blockers?
that's the goal. And our company is right now pretty much most of our customer collaborations have been kind of private, collaborations like this one. And the benefit we get is very much what I just described: is learning, making improvements up and down the stack. At some point in the near future, we'll be opening up our platforms for more general purpose, like public access. And by having done these sort of private beta partnerships, we should be able to offer a much better product and service than we otherwise would have been able to go do if we had not, gotten that learning and made those improvements.
So when you're trying to go more public, are you envisioning just like a cloud interface that people come straight to you, or maybe like one of the providers?
Yeah, I think that's how we've seen most, not just quantum computing, but computing over the last decade has really kind of migrated from, on-premise proprietary infrastructure more towards public cloud services that people can spin up and spin down instances on demand, pay for what they need as they go. And so we'll just fit right into that existing infrastructure and business model.
Hmm.
We'll be able to offer our platforms directly to end customers who want to engage with us in a direct relationship, and we'll also be announcing partners in the near future of major name brand cloud service providers that will have our systems available through them as well.
Oh, cool. Okay. And do you currently have do you have emulators then that run that you envision people learning on first before they actually touch
We
hardware?
do, and that's where we got started with our
Hmm.
customers. Early on was an emulator so that they can take an algorithm, they can write the code, or just take code they've already written for someone else's platform. They can compile it to our system. They can run it on an emulator, and it can tell them, is it compiling correctly? Have you written the algorithm in a way that it'll fit in our system or the specs of our system? Are there optimizations that you could do to improve the way you've written the circuit? That's kind of the benefit of the emulator, is it gives you some hints as to how you can write a better program that'll run best on the hardware.
Yeah. So with a project like you have going right now, I'd imagine you're getting a lot of real world torture testing, right? Real results to.
Yeah, that's the objective, is to get some real world testing, and things don't always have to go well to get learning out of it, right? You learn from the failures as well.
Yeah, absolutely. And what other collaborations does Atom Computing have going on right now?
We're not announcing any other collaborations today, but I would say that there are a mix of collaborations going on with government entities in the U.S. and around the world, as well as enterprises. What we kind of see today is governments leaning in, right, through Department of Energy, Department of Defense. There's a number of very capable teams that have been spun up that are either already, producing or exploring quantum applications, or kind of getting started up to go do that. And so a lot of those entities have been very eager to work with us, and we've been eager to work with them. So that's a good source of collaborations. I think publicly we've announced a DARPA collaboration that we have in the US to QC program, so that's progressing well. But we also see a number of enterprise customers who are wanting to be kind of early adopters of quantum computing and get an early mover advantage or first mover advantage in that space. And so these are, banks and automotive companies and transportation and aerospace and, large name brand companies that typically in their CTO office, they have maybe a 1, 2, 3, 4 people on a team who are QIS professionals who are looking at algorithms and applications that are pertinent to the mission of whoever their company is that they're working for. And they're already using time on, a variety of quantum platforms that are available publicly today. And, and starting to figure out how they can get benefit, when can they get benefit, how big do the systems need to be. They're providing feedback and requirements back to us and our competitors to help us make sure we're hitting the right design targets and that kind of stuff. So we're encouraged by the mix of enterprise and government customers that are out there. I think we're definitely, I would say, supply limited and not demand limited right now in quantum computing. There's a lot of people that want to program quantum computers. They want bigger ones and more capable ones. And that's us and others are, out on a mission to try to make sure that happens.
So you hinted earlier that it's, while there's 100 qubits now, you're not really quite ready to publicly state, I guess, what the next system will have. But could you give some sense of like what a roadmap looks like for the months or years ahead?
Yeah. Well, if we want to get to fault-tolerant computing in a time frame that's reasonable and going to keep people's attention, then we need to be scaling by more than a few dozen qubits each generation. If we scaled by a few dozen qubits, or was even just a linear scaling, it would take us forever to get there, or maybe not forever, but 20 years or something like that.
Yeah.
The math, right? And I don't think that's really what people have in mind. So we would love to see us get to fault-tolerant quantum computing within this decade, before 2030. We think that's definitely feasible. But if you do the math, you're going to have to add, hundreds or thousands or tens of thousands of qubits each generation. And so our roadmap looks a little bit more like exponential scaling than linear scaling. And so we're trying to make sure that we're adding a substantial X factor of number of qubits each generation. And with the architecture that we've chosen with the neutral atoms and having these things in a single module within a vacuum cell, controlled by pulses of light, which can be easily divided using optical devices, we think we have the technical roadmap to get there. A lot of hard engineering work ahead of us to make it happen and prove it. But I think the science risk has largely been retired over the last couple decades, and now it's just the hard engineering work on the software and the hardware to make that happen. So that's what people should expect from us, is something more like an exponential increase every generation. And then we'll see what our pace is between generations. We have our objectives, but until we do, we won't know that we really are on pace for what we want to hit.
So with like anything else, if you're cramming more qubits into one space, I guess all the control circuitry goes up, right? In one form or another.
Yeah, I mean, unlike superconductors or something where you have like one RF channel per qubit, we're able to address our qubits in parallel. So, we can address rows or columns of qubits in parallel, and over time we might be able to do full planes at a time and things like that. So the RF channels that we need are tied more to the parallelism that we get out of the platform. So we're talking, dozens of RF channels for a system, not hundreds or thousands or tens of thousands of RF channels.
Oh, well, yeah, that definitely helps with scaling.
Yeah.
um, and what would you see as, I guess, an obstacle to reaching fault tolerance? Is it the error correction?
Yeah, I think there's a lot of things. First of all, you need a lot of qubits. Well, you need a
Hmm.
lot of physical qubits, right? Because there's this yield between the physical qubits that get mapped down to logical qubits.
Hmm.
And every architecture will be a little different. And, is it 100 or to 1 or 1,000 to 1 or
That's what I
10,000 to
was
1,
hoping
whatever it is,
to,
right?
yeah, get an
But,
opinion on.
but there is going to be this yield. So you need a lot of physical qubits.
Hmm.
You need mid-circuit measurement in order to be able to, take readings as you're progressing through a circuit and detect errors and retry or redo things or correct things as you go. If you do detect an error, you're going to need the error correction algorithm itself. So what do you do if you do detect an error or a potential error? You're going to need long coherence times so that as you're progressing through the circuit, a deep circuit, and you're performing error correction, which is a feedback loop to a classical system, you're going to need to be able to hold that quantum information for a very long time. You're going to want high fidelity so that you're not getting a lot of errors in the first place. You're going to want great gate speeds and readout speeds so that as you're doing, large, deep circuits, that it gets performed in a reasonable amount of time. I'd argue you want parallelism for the same reason so that you get more done in one time step. So there's lots of sort of elements of performance that'll go into fault tolerant computing, and we'll have to not just check the boxes on all of them, but improve all of them as we go every generation to make sure that we're continuing to deliver the performance out of the systems that customers are expecting. Not just accurate results, but accurate results in a small amount of time.
Yeah, that makes sense. And of course, these are the challenges everyone's facing. I guess I was hoping to hear if there's any particular edge that neutral atom has for any of those areas in particular.
Yeah, I mean, we've demonstrated record coherence time, so tens of seconds on every qubit. That's different than other modalities, so that's a real distinguishing characteristic for neutral atoms. The
That's forever.
scalability,
Yeah,
yeah, and
basically, yeah.
at tens of seconds coherence, it's just so ridiculously long. It's a don't care,
Yeah, exactly.
right? So other modalities are trying to improve that and catch up on that, but we've kind of already got that one. I can tell you our second generation systems are even better. So
Wow.
it's like that one's kind of like we're good there. Scaling up to number of qubits, we'll have to show the world we can do it, but I can tell you we're doing it, and we're excited about that. So I think that's an advantage, is the scalability. I think fidelities is an area where the neutral atom community is catching up, just because we haven't been at it as long as like superconductors and trapped ions have developed pretty good qubits from a fidelity perspective. So we're playing a little bit of catch up there. But I don't think there's any architectural disadvantage or anything other than just cleaning up the noise and making sure these systems are high quality and reliable in order to go do that. So that's just work that needs to be done. Yeah, and then I would say like error correction, algorithms, mid-circuit measurement, those kinds of things, I think everyone's kind of on equal footing. We'll all have a little bit different way we go about it given the architecture and the sources of the noise, but I'm not sure anyone has an advantage or disadvantage there. That's just work ahead of us that needs to be done.
So far, it sounds like the next generation machine is going to be quite an announcement.
We're really excited about it. It's
Yeah.
not too far off on the horizon now, so we'll definitely give you a call back and see if we can update your audience once we are ready to do that.
Terrific. So you all heard it here first. Yeah, there's something coming. So yeah, Rob, thanks so much. I really appreciate you coming by to tell us about all this.
Yeah, it was a pleasure. Thanks for having me.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Neutral atom quantum computers differ from trapped ion systems in that the former have no charge and are trapped with optical tweezers in free space in a vacuum. Without a trap device, as used in trapped ion systems, neutral atom quantum computers should be able to fit many qubits in one system. How many? Maybe millions. And they're relatively noise-free qubits too. The atom computing system available now has 100 qubits, with a next-generation device on the horizon. Atom computing has been working on a collaboration with the U.S. Department of Energy's National Renewable Energy Laboratory, or NREL. The lab has a digital twin of the U.S. energy grid, which simulates nodes, switches, transformers, and so on, using an HPC cluster. Atom computing has added its quantum system to the mix. The hope is to come up with ways to optimize the grid and energy delivery. It's a complex problem, well suited to quantum computing. And the learnings from the project should be applicable to other types of networks, such as telecom, transportation, supply, and logistics. The problems solved with the digital twin are still only subsets of a large beast, but the hope is to expand the types of solutions as more qubits become available. Atom computing also hopes to provide access to its systems via the cloud soon, so you'll be able to take a crack at them without wearing an NREL lab coat. That does it for this episode. Thanks to Rob Hayes for joining to discuss atom computing, and thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.